have some news from PASS, as we always do. We'll get through this as quick as possible so we can give Bob as much time as we can. So here we go. So some exciting news from PASS is that they're going to be launching their new brand and the website to reflect the growing community of data professionals. Make sure you check out the website, look at the local groups and leaders and the virtual groups and virtual group leaders. New look, new names, but it's the same people running it. The PASS e-store is still open for the Summit swag if you haven't gotten it yet. The mugs are actually really good. I got 2 of those, and they actually hold about a good 16 ounces of coffee for all of you caffeine junkies out there. Some upcoming virtual chapter meetings later today. You're going to see, or actually, I'm sorry, it's already passed, but the PowerShell meeting was this morning. We have Women in Technology on January 21st. Saturday Night SQL is always a fun one to attend for Power BI. Here's some other virtual chapters. Again, we won't go through all of these just so we can save some time, but check them out if you have a chance. Here's some of the virtual chapters that PASS offers. This is not all of them. There are tons of them. Any facet of SQL Server you're interested in, there will be a virtual chapter for. Check them out. Sign up. It's free to attend all of these. Some SQL Saturdays that are upcoming in U.S. and Canada. We have the Cleveland coming up on February 4th. Denver, that's the BI edition in Boston. Overseas, we have Vienna and Pordenone. Again, check them out if you can. And as always, PASS is run by volunteers. If you can, we always love to have extra help. Volunteer today. Here's the site, volunteer.sqlpass.org. And stay involved. It's always free. We always like to do it that way. So with that being said, we're going to get ready to get Bob on here. So what we'd like to do, folks, is we would like to keep the questions until the end. This way Bob can go through all of his material. If you ask your question in the virtual chat or inside of GoToWebinar, I will have Bob answer them at the end of the talk. Again, we're going to reserve about 10-15 minutes. So put them in there. I'll have Bob answer what we can at the end. Bob, are you ready?
I'm ready.
Okay, here we go. I'm going to make you presenter.
Okay.
All right, you should have control.
Let me see if you can you see my screen, Jim?
I can see it. We're good to go.
Perfect. Let's go ahead and just start the presentation. Hey, thanks for everybody coming today, and just thanks, Jim, and the folks here in the In-Memory virtual chapter for inviting me to speak on this topic today. As Jim said, my name is Bob Ward. I'm an architect for Microsoft and our product teams, specifically in a group called the Data Group, and we own a bunch of technologies in the Data Group. Just about anything data related we own. More specifically, I work for a group within there called the Tiger Team. We focus a lot on SQL Server, SQL Hybrid, R technologies, HD Insight technologies, a lot of different technologies. And one of the things we do in the Tiger Team is branding and evangelism and training, like educating the community on very important topics to do with things like SQL Server. So last fall at the SQL PASS Summit, I did a talk, a very long talk, on SQL Server In-Memory OLTP at a very, very deep level. And Jim and the folks of the chapter were kind enough to reach out to me and say, hey, Bob, I heard you had an amazing talk at PASS. Our virtual chapter would love for you to come in and talk things at a more fundamental level on this topic. And then maybe at some other point you can come back and talk about all those gory details you presented at PASS. So I was excited for that opportunity to kind of take a topic and make sure that you kind of understood more about what is this thing and why would I even want to use this? What's the value behind this? But I can't help myself. There's probably a few things in the deck here that are pretty detailed, so I'll have to be sprinkled in a little bit. But the good news is if you look at my screen here where it says decks and demos at aka.ms/bobwardms, this talk that you're seeing right now is already available on that site along with my demos. So anything I demonstrate today, this deck itself, are already up there. And in addition, the deck and demos I did at the PASS Summit last year is up there as well. So that's something you can go look at afterwards. And maybe perhaps another time we can come back as this community learns more about this technology and do a little more advanced session. So just a couple of things on my contact information here. There's my email address. If you have a question today that does not get answered, or maybe you think of something later about this technology, I love to take questions on this technology. So just send me an email, bobward@microsoft.com, and we'll have a conversation about it. There's my Twitter handle. I'm not a Twitter expert, but I do try to get on Twitter and talk a lot about SQL Server and evangelize topics, so you can follow me there. And then if you want to, you can get some interesting information on a blog that I run called the Bob SQL blog. You can just search for Bob SQL or hashtag Bob SQL. And myself and Bob Dorr, another developer in SQL Server, we blog about some very interesting topics on SQL. So let's get started with this talk here. Today, basically, we're going to do two fundamental things, as you see on the left side. We're going to talk about what is In-Memory OLTP, what is this technology, and why do we do it? I mean, why do we actually put this type of functionality into SQL Server? And then we're really going to talk mostly about how do you use this thing? I mean, what are the particulars of how you go use the technology, with a couple of interesting demos to kind of show you the power of it. And then if we have time, we want to make sure we get your questions in, but if we have time, we'll kind of tease you a little bit about the advanced part of it by showing a little bit of how it works behind the scenes. Now, this is all based on SQL Server 2016. This feature in SQL was actually introduced in SQL Server 2014, but 16 actually is a step up, an upgrade really to what this technology can do. A lot of limitations were removed, performance was enhanced. So if we're thinking about using it, yes, it works in 2014. We have many customers make that change and go to it, but SQL 16 really makes a game changer when it comes to using In-Memory OLTP. So let's get into the what and the why. If you see this symbol underneath here and you're asking yourself, what is that symbol right there? That is the Greek word for 100. And that is really kind of the symbol behind In-Memory OLTP from a perspective of how we built this and designed this product. Well, why 100? Because the original goal of the developers that thought of this technology is they sought to make OLTP transactions 100 times faster, hence the name hekaton. So this is the Greek word for hekaton, and hekaton actually means 100. And so when you see the name hekaton throughout this talk today, and maybe some people talk about this technology as hekaton, now you know the history behind. You know, why did they come up with hekaton? Well, it was because we wanted to make SQL Server run 100 times faster for OLTP transactions. And this isn't something we just dreamed up overnight. Other people in the industry have actually looked behind the scenes on how to make OLTP a faster technology. So you can see some research has been done here, and there's a paper published in the ACM SIGMOG about, you know, a study about how you could take transactions within a database, a relational database, and make them faster. And it was all about optimizing paths within the code involving transaction logging, locking, latching, buffer management. And you're going to see those themes throughout here in this talk today about how we've done that with SQL Server. And a little bit of the history here, we actually talked about doing a concept like this way back in 2007 in a project called Verde. And that led to some early discussions and designs of this code name Hekaton in the 2009-2010 timeframe, which led to the release of In-Memory OLTP in SQL Server 2014. And then I particularly like this moniker of unleashed. We kind of unleashed the capabilities of this technology now in SQL Server 2016. Why do we do this? I mean, why actually consider going down this path of trying to make OLTP transactions in memory? Well, number one, we need to keep this product relevant in the world of high-speed hardware. When you start talking about hardware technologies to run database transactions with dense cores, fast I/O paths, inexpensive, massive amounts of memory, that's really the big key here. We need to take a look at SQL Server's transaction paths and how we ran transactions to say, how do we make this fast? And really it comes down to this. You know, people are used in terms of the database industry looking things in terms of milliseconds. We needed to make sure we took a look at running OLTP and transactions at microsecond speed, something less than a millisecond. That was kind of one of the original goals we were looking for. And how we kind of try to achieve that is try to figure out how to reduce the number of instructions, of actual computer instructions we have to run to execute a transaction. We have to find areas of latencies within transactions and reduce the footprint. We need to consider techniques like multi-version optimistic concurrency. I'm going to talk about what that is today. And things like lock-free algorithms, areas in the code where we have to do locking for data structures in our code. We have to find ways to actually make that lock-free, what we call lock-free. And other techniques like using dynamic link libraries and something called native compiled procedures to actually make procedure execution as fast as possible. So these two acronyms I have down here, I put here for a very important reason, because you're going to see them sometimes visible within a dynamic management view perhaps, or within a talk like I'm doing, or some sort of thing you might see in SQL Server. So one is called XTP, and if you want to know what that means, that's a code name we were using as we were developing this. and that stands for Extreme Transaction Processing, and HK, meaning Hekaton. So if you see these two acronyms, you'll kind of know they're all related in terms of In-Memory OLTP. You know, but I'm a big believer in just showing things. I mean, you know, instead of just having a bunch of slides where you're going to talk about something, sometimes people learn mostly from seeing things in action. So let's do it. Let's do that. So I happen to have some demos, very, very small little demos I'm going to show you, and I'm going to use perfmon and to show you kind of the differences between running transactions for In-Memory OLTP and then just standard SQL transactions. And I'm going to monitor two things here in perfmon. I'm going to look at batch requests per second. That's a common thing I'm going to look at to see, you know, how fast something is running to try to run multiple users in these transactions over and over. I'm going to look at page IO latch weights, and lock requests. Now the reason I'm going to look at those is because one of the big selling factors of In-Memory OLTP is that it's lock-free. And we've tried to remove the concept of SQL Server latching that we need to do on things called pages and locks as part of running these transactions. So I'm going to observe the behavior of transactions that operate in this way, from a normal SQL transaction to an In-Memory OLTP transaction. And for this demo, I've got some fun names here. I've got a database called Go Packers and a database called Go Cowboys. Now, for those of you on the phone that are football fans, you might have guessed that I probably built this demo before this past Sunday's debacle, where the Cowboys didn't get beat by got beat by the Packers. And if you're a Packers fan on the phone, you're probably cheering for the fact that they won. So I use fun names like this. Basically, you'll see two differences in the tables here. The table inside Go Packers is a standard table with an identity clustered index, an identity column using a clustered index, and just a character string. And for the Cowboys database, I actually have a table here where I've got the same thing, except I've added this keyword, memory optimize on, and a durability. This is one of the things that you need to do when you're creating an In-Memory OLTP table, or what we call a memory optimized table. So the code here is the same. Database is the same. The only difference here is this keyword of memory optimize on. So let's go run a couple of demos of what this looks like. I have some scripts here that kind of automate this. So I'm going to run a procedure that inserts data into this table with the Go Packers demo. And when I run this using a program called ostress, you see here that one user actually runs in like 1 second. And if I go to 2 users, you're going to see it'll come back in a certain number of seconds. It's like 2 seconds. But when I go to 4 users, you're going to see things change a little bit. Things are not going to run in 4 seconds. They're going to take a little bit longer. And if you go look at perfmon, you're going to see some interesting behavior here. You're going to see certainly a batch number of requests per second that run at a certain rate, like in this particular case about 170. But notice that the page latch weights get pretty high and lock requests get pretty high as I'm running these transactions. And if you look back here at the demo, notice that the 4 users took about 6 seconds. And if I go all the way to 8 users here, I'm going to see even a higher rate of page latch weights per second. And I'm not going to see much of an increase in batch requests per second. You know, I'm maintaining actually this kind of ragged type rate here of the batches that I have. Notice that the average here is somewhere down in this range, but I never really got above 200 per second. And if I look back here, it took like 11 seconds to run these 8 users. Now the Cowboys database using this memory optimized table has a different behavior. Let's actually go run it with 1 user. And if we run it with 1 user, I'm going to get back 1 second, similar to the other transaction. If I run it with 2, you're going to see the behavior go about actually a little less than 2 seconds. If I go to 4, you're going to see how quick we can actually run this compared to the other one. Now it's in 3 seconds, and if I go all the way to 8, you're going to see it takes less time than it did to run the standard transaction. And if you go back here for the perfmon, notice the big difference here. You see the blue line for batch requests per second, which I'm in the average about 220 now, and I got about the same batch requests per second running any of those number of users, concurrent users, but notice there's no locker latches at all. This is completely what I call a clean perfmon here, where I don't have this concurrency that I would have in the case of a standard transaction. In fact, it took 7 seconds. And what's really great about this technology, because it's in memory and because it's optimized, is it's very scalable. So as you add the number of CPUs and you add the number of users, your scalability actually increases. Whereas if I go to the standard SQL Server transaction without In-Memory OLTP, you're going to find that you're going to run into certain contention points with latches, locking, and transaction logging that's going to actually hinder your ability to be scalable. So that's just a quick look at what it looks like to run transaction in this space. It's a very simple type demo, but it actually shows you the difference and the power between what we're doing to avoid some of these contention points for things like locks and latches. Let's go back over to our slide deck and talk a little bit more about what this technology actually is. So what is it really? What are we actually doing here? Well, I look at it as In-Memory OLTP is made up of these components. First of all, you may have been used in SQL Server to building file groups. You have a standard primary file group with the database in SQL Server, and when you use In-Memory OLTP, you still have that standard file group because you still may put normal disk-based tables in your database, and we have to have a place to store schema or information about tables, and with In-Memory OLTP, you still store schema about the table. But for In-Memory OLTP, there's a special file group that must be added to your database. This is one of the new things you have to do to use this technology. In fact, it's the first thing you have to do. And there's examples in the documentation, and I'll show you an example in a second later on in my second demo about how to do that. So you add this memory optimized file group, and inside this file group, actually we store a series of files called checkpoint files. What you'll do when you build one of these file groups is you'll simply give it a folder name, one or more folder names, and in there SQL Server by default will write these checkpoint files. For In-Memory OLTP, there is no MDF file. There is no there is an LDF file for the log, but there is no MDF file specifically for In-Memory OLTP tables because they're in memory. And we'll talk later about what's the importance of these checkpoint files and why do we need them. So that's the first thing. You need this file group. Second of all, you have the actual memory optimized tables. And as you saw in the example I showed you, you create it just like a normal table, but you put that special keyword in there to tell us that it's memory optimized. And so it's going to feel like a normal disk-based table to you, but the big difference is it's all in memory. Internally, it's completely different. You're used to maybe seeing in SQL Server tables that are made up of pages that we construct and that we store pages on disk in an MDF file and that we keep in memory. Memory optimized tables are not made up of pages. They're made up of different types of internal structures that we do based on rows in memory. And we'll talk a little bit later about, how do we actually store those rows on disk when things are not in memory. But think in terms of these like normal disk-based tables that are all in memory. Internally, you don't know the difference, but we're actually storing these differently, okay? In addition, there are indexes with memory optimized tables, and you have a traditional non-clustered index, which is actually structured differently than the normal B tree of a table, but you have a new construct called a hash index. And a hash index is a concept where we're going to store information about this index in memory, and we're going to do it in such a way that it optimizes single row lookups, if that's the kind of type application you're going to use. You must have at least one of these indexes, but you can have multiple indexes. You can have multiple hash and non-clustered indexes for one of these tables. The third component, and this is optional but not required, so the first two components are required. You have to have a file group, you have to have memory optimized tables to use this technology. In addition, if you want maximum performance, you will take a T-SQL stored procedure and you will turn this into what's called a natively compiled T-SQL procedure. And I'll show you later in the other demo I have the syntax for actually doing one of those. When you do that, SQL Server will take your stored procedure when it's created, and in terms of the word compiled, it literally does compile it into a dynamic link library that is loaded into memory, and when we need to access these memory optimized tables, SQL Server will use this DLL to do its access. And it greatly speeds up query processing, because even though we still use standard SQL Server query processing to compile this procedure, when we need to access our data, the internal query tree that you're used to hearing about is now all baked inside this DLL, making things extremely fast. It's optional though. You can use SQL Server with memory optimized tables with standard query processing. You don't actually have to use these native procedures, but if you want the maximum performance possible, this is something you can consider doing. And then finally, there has to be code to run all this stuff, to actually support this technology. So the fourth component is actually the code we've built inside SQL Server, and I affectionately call this an engine within an engine, and it's made up of three components: a runtime engine, a compilation, and the actual engine itself. And these three things together, notice that HK acronym I'm using, these pieces together, which are actually DLLs running in SQL Server, they actually make up what we call the Hackathon engine. And they are actually code running in the context of the SQL Server engine itself, interacting with the query processor and the storage engine and high availability technologies to make it seamless to you. but they actually are internally different inside that Hackathon engine. And one of the key components is that all the code inside that engine is latch and lock free. There's no locking, there's no latching involved. So when things run in the context of Hackathon, our Hackathon engine, we've made it in such a way that it's extremely fast, extremely scalable, because it's latch and lock free. But we're still dependent on technologies like SQL OS. SQL OS, which is built in the engine to handle threading, memory management, those type of things. Hackathon still does rely on the fundamentals for that. So when you think about In-Memory OLTP, it's really these four things. It's a file group, it's a set of memory optimized tables in a standard SQL database, it's optionally natively compiled SQL procedures, and it's the Hackathon engine that's powering all to make this successful. Okay, one of the ways to look at what this is, I think, is to compare how it's different from normal SQL Server. So let's look at these three type of areas, and I think it'll help answer some questions like, I'm still not sure I quite understand what this is. Well, first of all, these memory optimized tables, I said they're stored in memory, but the data that makes those tables is stored in memory separate from the normal SQL buffer pool. Now, you have to make sure that if you're going to use this technology that all your data fits in the available memory that you have. That's one of the key decisions in using this technology, is that all the data I'm going to put in here, will it fit in memory? Do I have enough memory on my computer even to store memory for my table? But if you do, this is where the power of the technology comes in. Now, SQL Server actually will control the amount of memory that memory optimized tables will use to a certain extent, but if you want to have further control of that, you do have resource governor settings where you can actually control how much memory does In-Memory OLTP take up versus how much the buffer pool for standard SQL Server pages take up. Now, here's one of the key points here. When you run SQL Server with disk-based tables and we store things in pages in the buffer pool, really the MDF files are kind of like a paging system, right? When we're low on memory pressure, we'll take pages related to SQL Server tables and we'll make sure that any changes to them are written on disk. And if we can't find a page in the buffer pool memory for a SQL table, we'll just go read that page from disk and bring it into memory. In-Memory OLTP, memory optimized tables don't work that way. Everything has to be in memory. There is no paging system. You're going to find here in a second when we talk about I/O that the checkpoint files we use are simply used to increase and improve the speed for startup processing. They're not used as a paging system because everything is actually in memory. And as I said earlier, the table data uses different internal structures. There is no such thing as a database page. So think in terms of this memory that you have inside SQL Server for your normal buffer pool for disk-based pages and a separable memory area in SQL Server just for memory optimized tables. And notice this important point here, that when you start up SQL Server or when you start up a database that has memory optimized tables, all the data for that memory optimized table is loaded into memory at startup. And we'll talk about actually how that's loaded a little bit later. So that's how memory works. I/O is also different as well. So because of the fact that we don't have this paging concept and that pages can't get read out to disk just because you're doing lazy writing or something, the only time we have to actually log something for transactions for In-Memory OLTP is at commit time. So as you're running a bunch of different inserts or updates or deletes, nothing has to get logged until the transaction's actually committed into the transaction log. That can greatly speed up just your normal DML operations. And as I mentioned earlier, we actually write these things called checkpoint files out to speed startup. So there's a separate process to checkpoint data for memory optimized tables, separable from the normal SQL Server checkpoint processing. There's a separate process to write out data for memory optimized tables to these checkpoint files, but the only reason we do that is to speed up startup. As I said, all data has to be loaded. If we didn't have checkpoint files, we basically would just go read the entire transaction log, right? We could just read all the committed log records in the transaction log and load all those up into memory as actual inserts or deletes or updates into tables. But not only is that not fast, but it also prevents us from being able to truncate the log. So we still have the checkpoint concept, but again, it's only used to speed up startup and to actually put all those transactions into memory because we don't have basically the need to do undo recovery for memory optimized tables. Now we have this concept called schema-only tables, which we'll talk about in a second, and there's no I/O required for those. So if you have a scenario where you want to put a table in SQL Server in memory, and you really don't even care if it's saved anywhere. It's just this kind of table of data of lookup information. And every time SQL starts, you don't mind loading up this lookup information yourself. You'd have to go load it, and it doesn't persist restart. You could use a schema-only table, which is extremely fast. And one of the scenarios we'll talk about and show you a demo of is that this is an excellent scenario to replace TempDB type objects. And then finally, concurrency. This is one of the biggest selling points of this. There is no locking or latching required to run transactions for memory optimized tables. And we use this concept called optimistic concurrency, which means we pretty much assume that there's no conflicts that are going to happen between changes to these tables. Now, because of that assumption we make, that it's optimistic, you may have to add additional logic into your application for conflict error handling. We use a snapshot versioning concept to achieve this optimistic concurrency, and so we do use the concept of versioning with something called timestamps stored within the rows of these memory optimized tables. But here's the key point for you on the phone. We don't use TempDB. All the versions are stored in memory as part of the internal structures of memory optimized tables. So here's the concept of memory being different from disk-based tables. Here's the concept of I/O being slightly different for memory optimized tables. And here's how concurrency works that's different for memory optimized tables. So how do you actually go about the process of using one of the things? Well, the process is actually quite simple. First of all, you create a memory optimized file group, as we talked about earlier, and I'll show you an example of what the syntax that looks like. And then you decide on an index strategy before you create your table. You can actually tune that later if you don't need to, but it's better to decide ahead of time what that looks like. And I've got guidance for you to click on this link here later for choices we allow you to make this decision. And what I mean by that is you have to decide, do you need a hash index or a non-clustered index or both? And we do make some comments in the documentation. If you don't even know what a hash index is, and you're like, I don't know what that is, I don't know how to build one of these, then you can just choose a non-clustered index. But you're going to find if you really want to tune memory optimized tables, and you do a lot of single row unique lookups to your data, a hash index can actually be quite effective in making your OTP transaction very, very fast. Then you go create your memory optimized table with the syntax that I talked about. You create your table, you've already picked what indexes you're going to use, you add the indexes into the syntax, now this table is created. When you create one of these tables, we will actually store the schema of the table you created in the system table catalog of a standard SQL Server database. We also will do a checkpoint into those checkpoint files I talked about, and we will store some of the information about this table inside the checkpoint files and cells. That will be required when we need to start up the database at startup time to make things faster. Now, optionally, you can create a natively compiled store procedure. You don't have to. You can use standard T-SQL select statements or insert statements or even a standard store procedure. But if you want to make things fast and you want to completely avoid all this locking and latching I talked about, you would consider creating one of these natively compiled procedures, which there's a T-SQL syntax for, some additional syntax that's used to tell SQL Server to create one of these, and behind the scenes, we will create a DLL, and we will load that DLL into memory and use that as you're executing your transactions. And then you'll start running transactions, and then you'll go through a process of tuning the design that you built and managing it. You'll decide, was the indexes the right strategy? Is it as fast as I was looking for? Do I need a native procedure? Maybe I was not using one. Those are the kind of things and concepts you will consider doing as you tune and manage. And manage can be in terms of, do I need to use resource governor to control the kind of memory that's being used here? Are statistics being maintained properly? And I've got some other comments about that in a second. There's decisions you have to make as part of going through this. Number one, you have to decide, do you have enough memory? You may look at the tables that you're going to store inside SQL Server, and you're like, I'm not sure that I have enough memory to actually store these, all single in memory. Remember, everything has to fit in memory for a memory optimized table. This is not a scenario where you can say, well, I've got a computer that's got, say, 8 gig of RAM on the actual server, and I've got a table that's 12 gig. But normally SQL Server, that's okay, because for SQL Server, I may not even load all 12 gig of this table into memory, but even if I do, SQL's smart enough to read and write pages from disk when it doesn't have enough memory, no problem. But for memory optimized tables, all of your memory of the table must fit inside your computer memory, right? The SQL manages. So basically it comes down to estimating the size of the table, how much overhead is going to be required from indexing, how much overhead is going to be required from versioning. You know, you'll have to take a look at your transaction mix. Do you just do inserts? If you just do inserts and that's all you do, there is no versioning required. But if you do changes, updates, and deletes, then versioning will actually be part of the system. So when you do versioning with these changes, that will cause more growth of rows inside memory. And so I've got a tip and a link here in our documentation that's very excellent to help you go through the exercise of making some decisions on, do I have enough memory to store memory optimized tables? And then you got to make the decision I mentioned earlier about a hash or a non-clustered index. And again, you can use both. You can use more than one, but you must use at least one. And the typical decisions are, if you've got a lot of unique row lookups for a given column of your memory optimized table, then a hash index is actually quite effective. The only problem with that, there's some decisions you have to make when you build these hash indexes for something called a bucket count. And so it's a little bit non-trivial. There's some guidance in our documentation of exactly how to monitor this and decide what the right values are for this bucket count concept. But that's what a hash index benefits you from. If you do order bys or range lookups for queries in these tables, then you would use a non-clustered index. We also call that a range index. You have to make a decision on durability. So this is a very easy decision, but an important decision, and it can actually help make a huge difference in the speed of your memory optimized table. Let's say, as I mentioned earlier, you have data that basically when SQL Server starts, you have a process that will load up a table of memory, and if SQL Server restarts, you just run that process again to reload that. It's not data that changes a lot. Or, as we're going to see later in a temporary table example, you've got a tempDB type scenario. Remember, tempDB gets recreated every time SQL restarts. So you just temporarily keep results around in memory, a memory optimized table. Well, a schema only table would be perfect for you, because the only thing we're going to store is the schema of that table in SQL Server catalogs. There's no I/O required for those scenarios, not even transaction log I/O required. It's all in memory. But if you have memory optimized tables that need to persist server restarts and need to be durable, you would use this syntax schema and data when you're building your table. The example I showed you was a schema and data scenario earlier. And you have to decide if you use natively compiled stored procedures. And it really is the ultimate speed in these scenarios versus some limits. There's some T-SQL limits to what you can do inside these procedures, and you have to consider that when you're actually writing them. And I've got documentation for you to look at what are some of those limits look like. But again, to be clear, this is optional for you. You still can gain speed for memory optimized tables without using native compiled procedures, but the maximum speed for using that technology. The other important point is limited diagnostics by default. And what I mean by that is our dynamic management views and our query store feature in SQL 16 by default will not record performance information about these natively compiled procedures because that could affect the performance of them. There are ways to turn on the diagnostics, though, should you need to go do more debugging and troubleshooting to find out why wouldn't a native procedure run as fast as possible. But by default, we don't turn all that on to make sure we can run these procedures as fast as possible. And then finally, you do have some physical file placement considerations. Number one is the transaction log. Transactions in memory optimized tables only run as fast as the commit speed that you run them on for schema and database memory optimized tables. So if you're having a bottleneck and let's say you move to this technology and you say, look, this isn't as fast as I thought it was going to be. I thought it was going to be faster. Well, go take a look at transaction log speed, because maybe that is the one that's really holding you up. And in fact, I've got a pointer here to a new technology in SQL 16 SP1 with Windows Server 2016 called NVDIM, where we can achieve microsecond or faster speed in transaction log commits using this new hardware technology that SQL Server recognizes. So if you want the ultimate speed for transactions, you could consider using memory optimized tables in combination with this technology, and now the transaction log doesn't become a bottleneck anymore. The file groups themselves are important. There's one or more multiple folders allowed in that file group that you can do, and you are allowed to spread them across drives. But the speed consideration is only for startup purposes. All the checkpoint that happens for those files happens in the background while you're running your transactions. So what you care about is how fast can I go read from these files, and we'll do it in parallel if you create multiple folders across drives to kind of stripe the I/O that we need to go read all this data from these checkpoint files to load up your memory optimized tables when you start SQL Server. So those are some of the decisions you go through as you make the process of moving to this technology. And when we talk about migrating existing data, we've got some helpful things for you we've built into Management Studio. First of all, if you run a workload on a given disk-based set of tables for SQL Server, you can run something called the Transaction Performance Analysis Report. And I've got an example of one of these right here. And under the upper right-hand corner here, notice this was tagged as a minimal migration effort but a high gain for this table to move to memory optimized tables. It uses DMVs to make those decisions, but it's a report built into the standard reports in Management Studio. We have something called the Memory Optimization Advisor. Let's say you decide there's a table that's a candidate for this. You can then go in Management Studio, right-click on that table, run this advisor, and it will run through a checklist of things you need to do to migrate to this technology, and it even includes the ability to do the migration for you automatically. In addition, you could take a given stored procedure you're thinking about using for one of these tables in Memory Optimize, and you can run the native compilation advisor, and it will take a look at what things need to happen and to be changed in that stored procedure to move to a natively compiled procedure. And again, we do these based on DMVs. In the past, in 2014, this analysis report actually relied on the Management Data Warehouse feature, no longer. So if you have a workload that's active in memory and the DMVs can contain information about that, we will look at them and help make decisions in this analysis report. We recommend changes, find incompatibilities, and we'll actually do the actual migration for you for the schema, the data, and the procedures themselves. So here's some nice tips and handy things for you to use in Management Studio that help make migration from disk-based tables to memory optimized tables a lot easier for you. And here's some of the scenarios. Joost de Bruin, who's our lead program manager for this technology, and I've got a reference for you at the back of the slides of his Twitter handle to follow. He's documented about some of these type of scenarios to take a look at. If you really have the need for high throughput, low latency transaction processing, let's say you're running an online site that requires super speed for transactions, this is certainly a technology you've got to take a look at, right? Maybe you've got an Internet of Things scenario, you've got a sensor scenario where you're doing a bunch of data ingestion, and you've got this IoT scenario you're taking a look at for this new technology. This memory optimized tables could be, for you as well. We've had customers that do things like caching and session states. They build applications where in SQL Server they're actually storing information about sessions from like an ASP.NET application, and so memory optimized tables can get a huge boost in performance in just keeping that session state in our tables. And then if you're tired of TempDB, if that's a technology you're like, look, I use TempDB, but I'm always trying to fight it, migrating from the use of TempDB into memory optimized tables could be a huge benefit to you, and I've got a demo we're going to show you in a second what that looks like. And finally, staging tables. You may do a lot of ETL type operations, and you want to keep staging tables for the ETL. And if you know about staging tables, you've ever used this before, they're not things you care about persisting. You just use them for staging operations. They're just temporary. And so this is a perfect example where this might be really handy for you for ETL. So as I said earlier, let's take a look at a scenario where you could try to move from using TempDB to memory optimized tables. So same type of thing on my perfmon chart. I've got the perfmon chart up here, and I've got a particular script for you to look at here. Now here's an example already of using the special file group moniker for memory optimized data. And in this particular case right here, there's a name for this file group, and the file name is actually a folder name. So in this particular scenario, any checkpoint files are going to be written for this database, for memory optimized tables, will be written to this folder. We'll talk about we may have time to talk about the how it works slide where we mentioned kind of what kind of files are kind of placed here. But what you'll do is you'll literally see a series of files written in here. They're not MDF files. They're special files written, as I mentioned earlier, for the speed up of startup of memory optimized tables. So if you look here as well, I've got this HK using TempDB database, and here's a normal procedure using TempDB. You create your temp table, and here's something inserting data to the temp table in a loop. Well, here is a way to convert a TempDB scenario into memory optimized tables. We're not using TempDB at all. We're actually going to create a real user table in our database with the memory optimized option, but notice the durability is schema only. And the way we achieve uniqueness is we use your session ID or your SPID as a filter for the data. So by default, when you insert a row in here, we'll take your SPID and put it as a value in a table to uniquely identify your session's special data in this table. That's how you segment out which data is yours and which is not yours. And there's a constraint and a check constraint to line up when you use this data that I'll only see the data from my particular session. And the procedure is an example of this native compilation procedure. Here's the new syntax. You create a procedure with this native compilation, and you have to use schema binding. You have a keyword called begin atomic. You specify a transaction isolation level, and then you just run your transaction. And if you notice here, I have a delete at the end of this, and there's a good reason for that. That's because I'm inserting my data just like I did in my previous example, and the SPID's going to get added to it. But if you think about temporary tables, when you leave a procedure, they're destroyed. I need to delete the data that I previously inserted to kind of mimic what a temp transaction would look like. So let's go run this and just see the behavior. it's actually quite startling. Remember, this is a schema-only memory optimized table, so there's no logging involved. So if you use the repo using tempdb and you fire off, say, 10 users, they're all going to run that procedure using tempdb, you're going to start seeing the behavior. Batch requests are around like 500 to 600 per second. Notice a large amount of locks and page latches that are occurring. If you know anything about tempdb, when you do a lot of allocations of temporary tables, we have to potentially have contention on GAM, SGAM, and PFS pages. And this is a SQL 16 scenario where I've got multiple files installed here. So if I run the scenario and come back, this thing's going to take about 16 seconds. If you run the same repro using the hackathon tables and you run 10 users, you're going to see something really amazing actually here. You're going to see batch requests go up to over 1,000, and in fact, it comes back so quick that it only takes 2 seconds. So the difference here between 16 seconds for 10 users versus 2 seconds is amazing. And in fact, if I bumped up the number of users here for hackathon, I still can achieve amazing results. I can get up to 12,000 batches per second, and it comes back in 2 seconds. So this is all in memory, and there's no latch and locking occurring here. So you can see the power of taking a tempdb scenario, moving to a memory optimized table, and using the session ID as a way to filter out only your temporary data. And since it's all in memory and not logged, the speed is actually tremendous. Yes, there are changes you have to make, but imagine if you went into your application and looked at the use of tempdb in certain scenarios and started making that migration over, how fast really your application could become. So here's some management considerations for you. The fact that when you alter memory optimized tables, it does lock the table. It is used to maintain indexes, and it is a way for you to maintain this bucket count I mentioned for hash indexes. Also keep in mind that when you use natively compiled procedures, they're schema bound, which means you can't drop columns, for example. You'll have to actually drop the procedure first, then drop the column, then go back and re-add the procedure and make changes to it. We do support auto-update statistics if you're using the latest database compatibility level for SQL 16. So that's all supported like you would have a SQL Server. But natively compiled procedures are not recompiled when we do that. So that's another consideration of the limitation of those, is that you need to keep those fresh and compiled based on the proper statistics for your data. And then for managing memory usage, this is a common question I've had. Like, Bob, what if I use all this memory for my memory optimized tables and I need to reduce the amount of footprint? Like, I'm running out of memory. What do I do? Well, you got to delete data. It's all in memory, right? So there's no shrink involved here. The only way to shrink your table is to delete rows or actually drop the tables. We do use a garbage collection process to actually go remove deleted rows. So when you delete them, they don't delete immediately to reduce the space, but there is a garbage collection process that kicks in to actually do that. I mentioned earlier that if you want to manage the memory usage in a certain way to make sure you properly do that, you can actually bind your own resource gov in a resource pool with this store procedure to say, okay, I want to use memory optimized tables, but I'm using SQL Server disk-based tables as well, so I want to control specifically the amount that is used just for hackathon to a certain number. You would use a resource governor pool to actually do that. It's important to know that there are capabilities with technologies. A lot of people have said and told me before, hey, you know, I want to consider this technology, but it doesn't work with always-on availability groups. Well, that's not true. It is supported with always-on availability groups. Or maybe you've got a scenario, what we call a hybrid transaction analytical processing scenario, or HTAP, where, hey, I've got memory optimized OLTP that I'd like to consider, but I want to use column store indexes. Well, with SQL 16, you can use both. You can actually support column store indexes on top of this memory optimized table. Well, also you may say to yourself, really, I'm into the cloud, and I'd like to use Azure SQL Database. Well, late last year, we announced a complete support for memory optimized tables in Azure SQL Database, so that's something you can do. Or maybe you have the need to have transactions that both use disk-based tables and memory optimized tables. Well, you can do that with cross-container transactions. We've expanded the SQL surface area in 16 for certain T-SQL restrictions that happened before. It has complete backup restore functionality, and then consider this last point on my slide. You're only really limited by the memory you've got on the operating system. And in Windows Server 2016, we support 24 terabytes. So if you're looking at a scenario going, look, I do have very, very large tables I want to support with this technology, but I think I can't do that, well, consider the fact that you can have up to 24 terabytes of this in Windows Server 2016 in combination with SQL Server 2016. Let's just spend a few minutes here. We have about 15 minutes left in our talk, so let me spend about 5 minutes or so going over a few internal pieces of how it works. I can't help myself. Whenever I do a talk on technology with SQL, I got to put my geek on here and spend a little bit of how the technology works. If you see these slides and you want a lot more information about this, we can come back at a later session and dive more deeper into it, or you can go take a look at the past talk I did last year where I spent like 3 hours going into the internals of how this technology works. So first of all, just from an architecture point of view, we actually have a pool of SQL worker threads that are responsible for things like garbage collection I mentioned, for doing the special checkpoint I/O, and to do asynchronous log flushing for the transaction log. We actually compile native store procedures. I mentioned the DLLs, but in addition, anytime you create a memory optimized table, we actually compile what's called a schema DLL in addition. And this third point here, the engine runtime is agnostic to tables and rows, means that the Hackathon engine doesn't understand what a row looks like. It doesn't know the format of it. Unlike SQL Server, where in the row we actually store the formats of the data in the row itself, to make things really fast in Hackathon, we don't do that. We rely on the schema DLL or the native procedure DLL to understand the format of the data, which is why when you drop and create a table for memory optimized tables, we rebuild these DLLs. The DLL contains the knowledge of what row formats actually look like, table and row formats. The Hackathon engine runtime doesn't understand that. It doesn't need to. And that's one of the ways the Hackathon engine can be very efficient to be lock, latch, and even spin lock free. Now this multi-optimistic concurrency is really interesting. One of the key points of achieving this multi-version optimistic concurrency to be lock free is rows never change, they're immutable. So anytime an update is done, we always turn that into a delete and insert type operation for memory optimized tables. And then we keep versions of things. We actually use timestamps in the rows for correct visibility and transaction correctness. So everything, think in terms of snapshot isolation in SQL Server. That's the way you should kind of think of memory optimized tables. We kind of make the assumption that things are snapshot version based. So when you run transactions, you see things visible within your snapshot. We support other isolation levels within this technology, but we're always creating versions regardless. And another point is the versions are not in TempDB. There's no use of TempDB to store version information. Now this optimistic concept means we don't use locks. Pessimistic would mean you use locking. So we assume there's no conflicts. We use this snapshot versioning, and then when the transactions are committed, we do something called conflict detection. And this is why, and we document in our documentation, when you run an app, you have to be prepared in your app to see that conflict might have occurred based on your visibility of the transaction and take the necessary action. Maybe you need to retry your transaction is one normal scenario for this type of application. But that's how we achieve optimistic locking. Now, I thought you might find this slide a little bit interesting here. This is the path of a normal insert. This is how we get really fast. When you do an insert, we have to do an insert log record in the transaction log. We got to get locks. We got to latch the page, modify the page. We may have to update index pages, which could require more logging, more locks, and more latches, and then we have to release all of that. And then finally, when we do a commit transaction, we have to flush we do a log record and we flush the transaction. Well, this is what a memory optimized insert looks like. You basically insert the row in memory and then you maintain the index in memory. And in fact, there are no logging operations required for indexes. That's a really interesting optimization. The only thing we log are the changes made to the actual tables. Indexes are maintained completely in memory, so therefore when the database starts up for memory optimized tables, we rebuild those indexes in memory as part of startup processing. And then notice here, it's only at commit time that we have to actually go insert anything in the transaction log and then actually flush the transaction. So a much more optimized path to do these transactions. And keep in mind that as part of the normal transaction, you may have page splits. Any system transaction required, like a page split, requires a log flush, and there are spin locks throughout the use of these different paths. Whereas on the memory optimized side, there's no index logging, no latches, no spin locks, and that's how we're able to achieve the speed of which I showed you in those demos. And then schema only, as I said earlier, also is no logging, extremely fast. So from a checkpoint point of view, why do we have to do it? I mentioned earlier, we got to speed up database startup. We don't need checkpoint files simply to persist tables for memory optimized tables. We could use a transaction log, but if we want to keep the transaction log available for truncation and we want to make it much faster, that's why we actually write these checkpoint files. And so we only write data based on committed log records. We don't need to ever write data based on uncommitted log records because we only actually log things that are committed transactions. So anything that's uncommitted is in memory. If SQL restarted, those uncommitted records wouldn't exist, so we don't have to even worry about that. It's independent of SQL recovery intervals. And then I mentioned earlier about these checkpoint files. We have this concept called data and delta files, which are files based on inserts. Deltas are actually filtered based on what rows are deleted. So we have a way of merging these together to actually do the I/O for checkpoint processing. And this is kind of what recovery looks like. We read details from this special database page called a boot page. We load something called a root file from this checkpoint set of files, which has system tables and metadata information. And then we load a certain set of these checkpoint files called active data files, filtered by these delta files. And then we go in the transaction log and say, well, what transactions are committed in there that are greater than what we had in these checkpoint files? And we just run redo. So that's the simple process of recovery. It's simpler than SQL Server recovery, but here's the irony, it could take longer. The reason it could take longer is we have to actually load all the data from a memory optimized table into memory at startup time, because remember, everything is contained in memory, whereas a normal SQL Server table does not require that. Data can be loaded on demand as you actually go read pages. So here's my case for using this technology. We'll take some questions. Number one, my contention is, with the right way of designing the actual table, you can get a 30x boost in OLTP performance just by going to this technology from standard OLTP transactions. It's truly lock, latch, and spin lock free type of transactions. Native compile procedures can give you super speed, and you can do some testing where you can see the difference between using those and not using those. And even though it's fast, without using them, you can really get maximum performance using the technology. And then you can combine it with column store for a true type of what we call a hybrid transaction analytical processing type application, one that requires OLTP but also needs to do analytic processing on top of that data. And then finally, SQL 16 is a major step up from 14. So if you looked at SQL 14 and you thought this technology was a candidate for you, but it just didn't quite have everything you needed, take a hard look at SQL Server 2016 because I think it might have what you need. And I'm sure you want resources. Number one, follow Jos. Jos de Bruin is the lead program manager for this technology. Follow him on Twitter. See what he posts on Twitter about this technology. There's a plethora of resources for you to click on and link on afterwards. And again, the decks and demos of everything I just showed you are already available on this URL for you to take a look at. If you have any problem getting those, just email me at bobward@microsoft.com and I'll get them for you. And if you saw a little bit of the inside that I kind of briefly went over and said, oh, I want to know more about how that checkpoint works, I want to know more about how that hash index works, I want to know the structure of a row inside one of these things, go look at the inside in-memory past talk that I did. It gives you exhausting, gory details of all those kind of type things. So I really appreciate the chance to talk about this today. Let me put this slide back up because you might want to actually look at some of those URLs. And then, Jim, let's take some questions.
Sounds good, Bob. Can you hear me here?
I can.
Okay. So we did have a couple. The first one was from Radu. He wants to know, for the memory, does this fall under max server memory or for a SQL Server instance, or is it outside of that? So I'm guessing he means...
What a great question.
Yeah.
Great question. I need to add that to the deck. It does fall under max server memory. So max server memory controls all memory allocation. From SQL Server 2012 on, max server memory controls all memory allocations for SQL Server, aside from things like Windows threads and stuff. So max server memory is the memory allocated for max of SQL Server, and the memory for memory optimized tables is part of that equation.
Good question. The next one comes from Carlos. He wants to know, when the service is stopped, the data from in-memory tables are written to checkpoint files. Is he right?
So the answer to that question is that anytime we feel we need to checkpoint a database containing memory optimized tables, we will write data to files that we think as part of committed records in the transaction log. So yes, as part of stopping SQL Server, we do a checkpoint for every database. And if we have a memory optimized tables, we will write some data to those checkpoint files. We don't need to write all data. And the reason we need to write all data is some data may have already been written to previous checkpoint files, because checkpoint is a continuous process we do in the background. So some data may be written, but not all data written.
Okay. There was another question from Andre. I asked for more clarification. It says, what about clustered column store indexes? I'm waiting for his reply.
Just to let you know, those are fully supported with memory optimized tables. So column store index fully supported. You can use those in combination. A lot of good information out there about how to do that.
I believe that's what his question was going to be, because it came up when you were explaining about those.
Sure.
We did have a couple questions about if this is going to be available on YouTube. Folks, yes, this session was being recorded. It will be on the In-Memory Virtual Chapters YouTube channel later today, along with all of our other presentations. Bob, I don't see any other questions popping up. There are a lot of thank yous.
Their minds are still blown, Jim.
Yeah. Tell me about it.
They're still trying to absorb all of this. You know, really, Jim, I really hope, and folks in the audience today, I really hope the key here is that you heard enough from this talk to go back and look at this again, to say, you know what, I got to take a look at this. There is value here. And maybe the migration is not that bad. Maybe I've got a temp DB scenario that's really biting me in my environment, that's really hurting me. And, you know, I need to take a hard look. Maybe I should convert that to a memory optimized schema-only table with some small changes that I showed you there. And maybe all of a sudden my problems all go away just by making those changes. So, you know, take a look at these references. Take a look at the reports from Management Studio that help you look at your existing workload and make decisions. If you've got a scenario out there where you're just, let's say you've got a table that you're just pumping a bunch of inserts into a table. That's your part of your SQL app. If you're doing something like that, this is a technology worth taking the time, stopping and seeing, should I make a move to this, for sure.
We got two more questions. Actually, got a few more questions rolling in here.
Please, let's do it. We still have some time, right?
Yeah. We can go a little over if we have to, as long as you have the time.
I do, yeah, absolutely.
From Marcio, is there a DMV to track the size of the in-memory tables?
Yeah, the question is yes, there is some DMVs to track all the usage of your memory optimized tables and their memory consumption. So yes, they're all available out there. Top of my head, I don't remember the name of them, but they do exist.
Okay. The next question is from Paul. For analytical queries, is it a good approach for using this?
So the question is about analytical queries. So if you just have pure analytical queries and that's all you're trying to do, you may not have to move just to this. You should take a look at column store indexing, right? But let's say you have a scenario where you do require fast OLTP, like you have transactions that need to run really, really fast, but you have the need to run analytic queries on top of that. That's where the combination, and that's what we call HTAP, Hybrid Transaction Analytical Processing. That's a term you can look up. You can do it on your favorite search engine. And the combination of using this technology, memory optimized tables, with column store give you those capabilities. But if you're just looking to do analytical queries, column store index alone is really all you need to take a look at.
Awesome.
We should do a column store talk on this virtual chapter sometime, right?
Yeah, exactly. I think we have a few lined up, to tell you the truth. I think we have a couple that are coming. So it's one of the things we're going to look for. So a follow-up question from Carlos. How can we calculate the size of the in-memory table from an existing disk table, and is it more or less the same?
Great question, Carlos. So if you remember one of the slides I presented where I talk about estimating size, I've got a hyperlink on that slide that you can click on where there's a specific set of documentation to do the exercise you're talking about. And the answer to your question can vary a little bit. It may be slightly larger than what your data looks like inside a normal disk-based table, but it also may be less or the same. And the reason I say that is it depends on your design decisions and it depends on versioning. So for example, if you simply have a table that you're going to move over, and all you're doing is inserts on that table, and that's all you're doing, and let's say you pick a non-clustered index on top of that for memory optimized, it could be that for the most part the size is pretty much the same, actually. It just varies a little bit. Remember, internally we store this a little bit differently. But let's say you're going to make that same decision, but you're going to do a lot of changes to this table concurrently. Well, we've got to keep versions for all of that, and we don't keep it in tempDB. We keep it with the memory optimized table itself. So it could be that you could see a little slightly larger size because of those kind of type things. But again, there's a great page in the documentation that goes through an exhaustive checklist for you to help make those decisions.
So it's,
and by the way, our memory optimization advisor helps you make some of those decisions as well.
So it's that age-old answer for DBAs where it depends, right?
Yeah, but the good news is that you have some decisions in mind to help make some of those choices. Like if you're just going to do pure inserts, for example, that's all you're going to do. You just say, oh, I'm just going to insert in this thing. I think you can count on the fact that it's going to be pretty similar size, right? But it's versionings where I've seen this become more of a factor. Plus, it depends on what index strategy you pick. So there's a couple of decisions to make that could make it easier for you. But yes, unfortunately, you can't just say, oh, it's just going to be smaller or bigger.
Right. Well, Bob, I don't see any other questions flowing in.
Hey, Jim, do you have a way of saving all of those questions?
I do not, unfortunately. So
okay. But it's on the recording.
yeah. So I spoke too soon. Kevin made a comment. It seems like your example was reversed. The Packers were the more optimized team.
Yeah, he must be a Packers fan. And when I made this demo, I thought, should I even show this demo today? But I'm a good sport. It's okay. We got beat, so I'll show it. But yes, the Packers seem more optimized. I agree. I'm painfully saying that here on the recording. Somebody's going to go quote me on that on Twitter, I'm sure.
Yeah, we got it recorded, so you're stuck.
I'm stuck. Yeah, exactly.
So 2 more questions here, Bob. Like I said, as soon as I say no more questions, they come in.
No. Hey, let's get them all answered while we're on the phone.
Yeah, that's good with me. So from LJ, is it compatible to transactional replication?
That is a very good question. To the top of my head, I don't know the answer to. So that's one I'll have to look up. Email bob@microsoft.com, and I will get you back that answer. You could do a lookup yourself in our docs to see if it's mentioned in there, but I don't remember off the top of my head if we support transactional replication. I'd be surprised if we didn't, because transactional replication is all about replaying log records, but I'd have to go double check that to be 100% accurate.
Okay, I sent him a message asking him that just send you an email so you can work with him.
That'd be great.
So Carlos, he has a bunch of good questions here. He's asking,
we need to bring Carlos as a host next time into this.
I think so. Carlos, with all the questions you're asking, we're gonna reach out to you about presenting next.
That's right, exactly.
Is the past summit talked about isolation between disk-based tables and in-memory tables? Isolation tables, he means.
Isolation tables. Well, what the past talk will talk about is in depth of how we do concurrency. So you'll see visualizations of how versioning works, and you'll see how we use timestamps so you can see the visibility of a transaction. So there's a lot of good details about how that works in the talk. As far as the difference between disk-based tables and these tables, I do talk about isolation levels, but you have to have some fundamental understanding of what those are, like what is read committed, to look through those decks. If you have some more additional questions about that, Carlos, send me an email and we can have a conversation about it.
All right. So there are no more questions right now. So he says thank you very much. So folks, again, thank you very much for joining us today. I really appreciate all the attendance we had. I hope you all enjoyed the session. We look forward to having Bob back in the future on some more advanced topics. We now know he can do the beginner topics, so we're going to look forward to some advanced topics coming from him. If you have any questions for Bob, his contact information is in the slide. Again, we'll post the slides and the recording of today's meeting up on the website later today. And if you have any questions for us, you can always reach us at imvc@sqlpass.org. Bob, thank you again. It was a great session. We really appreciate it. Everybody else?
Yeah, Jim, thanks. Folks on the phone, Jim, thanks for the opportunity. I love being here.
Not a problem. Thanks again, folks, and have a great day.